Okay, so we're actually going into recitation number 2, problem number 5, I think. Yeah, problem number 5. So in this idea, right, so basically the question is, we were asked, right, to find something called the critical angle. And this is actually the critical angle for total internal reflection. It's a big word, right? So I'm not actually just solving the problem, I'm actually trying to teach you lectures and stuff so that hopefully I'm kind of reinforcing a lecture. But basically understand what's happening. So imagine we have two materials. And I'm going to make up these numbers, right? So because remember, we have a qualitative understanding of Snell's law. So here is Snell's law. Okay, and so basically angle of incidence and angle of refraction and related to the material N1 to N2. So imagine the following scenario, right? So here is N1, and I'm going to say N1 is actually lower index of refraction. So I'm going to say that N1 actually has a lower index of refraction than N2. So imagine the following. So here's our normal. Here's a light ray coming in. And you have to ask yourself, right, what's going to happen qualitatively? Qualitatively, right, there's going to be a point, right? So we have a choice. We already know qualitatively light likes materials with a higher index of refraction. It tries to go and stay in that material. So, for example, here's N2. We said N2 is larger, right? So when the light ray comes in, it still wants to be in this region, but so it doesn't want to be in this region because it's got a lower index of refraction, and N1 has a lower index of refraction. And so if I do a straight line right across the light ray, which my diagrams are terrible, but it's going to bend in this area because it's trying to get closer to this region as opposed to staying more into this region. So we're expecting this. If I take a steeper angle, this angle of refraction will be getting closer over to here. And if I keep going, right, there must be a certain point, right? A certain point where this is literally going parallel. The light ray is roughly going really grazing the surface of that material. And this angle, right, that we're given, right, this angle where this reaches that critical point, right, is called the critical angle. And it's a critical angle for total internal reflection. So because if I exceed this, right, at that point it can't go into this material, it'll actually start reflecting. So you have to remember again, so I start off at a certain angle, and then it wants to stay in the higher index material, so it'll bend in this region. And if I increase a little further, it'll still be closer into this region. And then as at a certain point, right, this angle will be 90 degrees. So this theta is the critical angle. And that critical angle, right, will deflect a light ray roughly parallel to the surface. Okay, so what you're saying is that N1 is whatever the material is, but theta 1, actually this is N1, theta 1. So theta 1 is 90 degrees. And this is N2 sine of theta 2. So theta 2 is really called the critical angle. So let's call it the critical angle. And so if I solve for theta 2, we'll see that that's equal to N1 divided by N2 is equal to sine of theta critical. And so theta critical is N1 divisible by N2 arc sine. And I'm sorry, So this is the equation I'd actually try to solve. So solving the problem, so if somebody gave you a critical angle and say index is equal to air, which is 1.0, and let's use water because N2, let's just do the critical angle for total internal reflection, that's what's called critical angle, and is equal to 1.33 because we did a couple of problems already. So this is the index refraction of water. So what's the critical angle for water? So that would be equal to arc sine of 1.0 divisible by 1.333, and to two significant digits. So let me bring out my calculator. So what is 1.0 divided by 1.333 equals, and arc sine is inverse sine, so inverse sine, and I get 48.6 degrees, which is really 49 degrees. So which means that about 50 degrees, if I exceed that, right, if I go and increase from 49 degrees to a little bit like 50 degrees, we'll get reflection. This is called total internal reflection. That's total internal reflection. So this is when we've reached a critical angle, we'll start reflecting stuff. Okay, so the critical angle is exactly the same as reflection over here. Anyway, so that's the main idea, and I think I was supposed to make another point. Oh yeah. Let's just make sure that you understand that critical angles only affect materials when you're looking from a light ray from the higher index material going into the slower index material. Once you see this, there is an angle called the critical angle, but it does not appear when you're looking at light rays from a lower index material going to higher index material. And let's make sure you understand that. And let me erase a couple of things. Actually, you know what? I don't think I have to. Let's just do it a little diagram because it takes too long. So here. So imagine that N1 again has a lower index of material than N2. So we're saying N1 has a lower index than N2. So is there a critical angle for going from a light ray, such as 1.0 to, let's say, water, which is 1.3? Is there a critical angle also for, just like there's a critical angle of light ray going in water into air? Is there such a critical angle of total internal reflection? Let's check. So here is our light ray. So here is light ray coming in. And the first thing you should notice is, as I hit this light ray, right, since N2 is a higher index material, let's draw a straight line going across. Is it going to come, does light ray going to go into this region or in this region? Well, light ray likes the higher index material, so it'll bend into the material. And if I basically try to graze a little bit further, right, so as I graze a little bit further this way, like over here, getting lower at this angle, so the angle of incidence is higher, you'll actually see it starts bending further into the material. And at a certain point, right, actually, I think I totally messed that up, didn't I? Yeah, actually. But the main thing is that, actually, this should be there. Actually, yeah, I did make a mistake on that, so it should be going this way, I think. Yep, I made a mistake. Anyway, but the main thing is that when light rays hit, right, they go into the material. So it's just over here. It goes into the material. So that's the main idea. So whatever angle that you come in, right, it always goes into the material, the light ray. So it doesn't reflect off. So there is no reflection portion. Actually, there is a concept later, right, that we'll mention, right, and actually has to do with electromagnetic fields, right, and how they actually, basically, there is a portion of the wave that's actually being reflected, and there's a portion of the wave that's getting absorbed, and that has to do with some more advanced material, and but you don't have to worry about it. But the main idea is that there is no total external reflection. It doesn't really exist, but actually, mathematically, and if you're actually going deeper into physics, there is a little light ray that is being reflected, and there's a light ray being refracted. Okay, so that's not technically correct, but for the lower level physics class, your intro to physics classes, the main idea is that light rays, when they hit a surface, they go into the material, and so there is no reflection. That's the basic idea you have to understand. So again, the critical angle that you should be looking at, right, is that as you increase the angle, this light ray gets closer and closer to the surface, the exiting light ray. And at a certain angle, to call it critical angle, this light ray can be effectively 90 degrees. And if you go a little nudge further, right, it actually causes total internal reflection. So that's called the critical angle. Exceeding the critical angle, you get total internal reflection. That's the main idea in that problem.